This webinar is being recorded. It will be posted on the Fillmore Group's website after the in a day or so after the webinar, so you can share it with colleagues if they weren't able to join us today, as well as the presentation materials that we'll be using. Everyone is on mute right now. Because of the number of attendees that we have, I'm going to pause occasionally for questions. And what I'm going to ask you to do is use the chat function that's part of the webinar, so you can post a question. When we get to those points, and then if we have some time at the end, I'll open the line for conversation back and forth, give and take. But we've learned before in prior webinars that there's a lot of ambient noise that tends to interfere with people's understanding of what it is that we're discussing. So with that, I'm going to go ahead with IBM Data Retrieval Technologies, RDBMS, BLU, Netezza, and Hadoop. This is the capstone in a 3-webinar series that Kim and I put together. The first was on the IBM DB2 Analytics Accelerator, PTF5 for version 4. And the last one that we did 3 weeks ago was on hybrid transaction and analytic processing. And then this sort of brings those technologies together with Hadoop, as Kim mentioned. So the objectives, and I did not update the material since I did the presentation in May at IDAA, the International DB2 Users Group. Not a lot has changed, so I figured that you wouldn't mind the branding. I want you to understand the technical differences between the IBM data retrieval technologies. If there are a couple of different ways to do things, if you have a hammer and a screwdriver and a wrench, which do you use in which case? And so that's objective number 2, is to help you choose the most appropriate tool for each business use case. And then finally is to articulate the value props and the pluses and minuses of each solution. So if somebody says, when are we going to start installing that Hadoop thing? You'll be able to say, well, these are the business use cases we've identified, and these are the ways that we'll be able to use Hadoop or DB2 with BLU Acceleration, but not in other cases. So the agenda today, brief introduction of the Fillmore Group. Why should you listen to us? We'll talk about RDBMSs. I'm assuming most everyone on the call knows what an RDBMS is or has worked with one in the past. It's sort of the foundational technology for most of e-commerce and the internet, as well as transaction processing for most enterprises. Then we're going to talk about Netezza, the Field Programmable Gate Array, or FPGA technology, that allows very fast scanning of data from commodity disk drives in an appliance. We'll talk about DB2 10.5 with BLU Acceleration. This is the DB2 that runs on the distributed platforms, Linux, Unix, and Windows. And then finally, Hadoop and the MapReduce technologies. So I have a quote from St. Thomas Aquinas: rarely affirm, seldom deny, always distinguish. And that's what we're doing today, is distinguishing between all these technologies and the ways in which you might deploy them. I am Frank Fillmore, DB2 Gold Consultant and an IBM Champion. Kim, whom you heard from before, is also an IBM Champion. The Fillmore Group works with dozens of experienced certified consultants. We provide information management consulting services to help you implement and deploy these technologies. The Fillmore Group is an authorized training partner and an IBM software reseller, including all of the technologies that we're going to talk about today. Yep. So the RDBMS. The characteristics of an RDBMS were first articulated, I believe, back in 1971 by Dr. E.F. Codd of IBM Almaden Research. It had to do with coming up with a organized means of managing data that was not tied to a particular vendor's hardware or operating system. So the data is stored in a tabular form known as relations, hence the name relational database. There are rows and columns. A row represents an instance of data, a customer, a patient, an insured, a student at a university, and then the columns are attributes or pieces of information, name, address, phone number, city, state, zip, salary, diagnosis, etc. One of the characteristics of the relational database is strong data typing. So unlike some of the data typing methods that were used prior to relational database management systems, something like the mainframe VSAM index file system, which did not have strong data typing, where you could have character data in a numeric field and got something known as a data exception or a SOC7, when you encountered that data, when you weren't expecting it. Strong data typing enforces that only numeric data can be found in numeric fields, no character data allowed, that dates are valid dates, no April 31st, etc. And we'll come back to this in a little while. I may be preaching to the choir and stating some things that are obvious to you all, but I want to make sure that you understand some of the differences, because not all the database or data management retrieval systems that we're talking about today exhibit these same characteristics. The way that I get access to relational database is through B-tree indexes. So I have a very sparse to dense hierarchical set of root pages, non-leaf pages, and leaf pages, and we'll see an example of that in a second. And again, it's going to be important to understand the structure of the index, to understand why that has not been able to satisfy data retrieval when we have tables in the billions or tens of billions of rows. And finally, the relational database uses a cost-based optimizer to choose an access path. So you in the SQL tell the database what it is that you want to retrieve, and the database determines how that's accomplished. Whether or not to use an index, which index to use, what join strategy, whether or not a sort performed. So examples of the RDBMS are from IBM, DB2 for ZOS, and DB2 for Linux, Unix, Windows. So I'd like to pause for a second with that introduction and give our first poll. One question, we want to find out which relational database solution that you run in production. And I'm assuming that the folks have the choice to answer more than one, because they may have more than one in production. You only get one answer.
Actually, the choices, I don't know if you can pull it up there.
Yeah, I can see.
Okay. Yeah.
Okay, we run them all. So there is an answer for that. So the poll has been launched. You should see popping up on your screen the opportunity to answer the question as Kim has posted it. So we're seeing some responses come in.
Couldn't think of the word heterogeneous, so I put down Heinz 57.
That's because you're from Pittsburgh.
Exactly.
I understand. So we're seeing a distribution just all over the map. It's interesting. So the responses that we're getting, about a quarter for DB2 for LUW, over 40% for ZOS, 13% for Oracle, 25% for SQL Server, and 50% is, our shop is like Heinz 57. We run them all. Okay, very good. Well, thank you all for your responses. So this is an example of the index that I told you about. We start at the top. I'm going to pull my highlighter up here. We start at the top with something known as a root page. The root page contains entries for all of the non-leaf pages below it, an entry of the highest key value and the location of the non-leaf page that contains that highest key value. So we have a non-leaf page here with key values of C and K. These correspond to the leaf pages that are below it. So in the very first leaf page that we have here on the left, the highest key value that is found is the letter C, and that corresponds to a RID or a row ID of the physical location of the data on a page, in this case, page 4023, slot number 2, so I can find that row. So very briefly, what I need to do, and there may be more than one set of non-leaf pages. I could have an index that runs 8 or 9 levels deep in some extreme cases. The rows are maintained, the key values, the records are maintained in strict sorted sequence on all of the pages. And if I go to insert a key value and there's no room on a page where it belongs, I need to split that page in two and put half the records on one and half on the other, which is how indexes grow, because as pages fill, they split. As they enter more key values in the levels above them, let's say the leaf pages at the very bottom, fill up the non-leaf pages, they split. We could create another level in the index, which means that every time I need to search for a key value, I need to do another I/O. I perform an input-output operation for each level of the index to walk the index to find the record that I'm looking for. Now, this works well for keyed values if I'm looking for a particular patient ID or social security number or date of birth or something like that. But if I'm scanning lots of records for lots of different characteristics, this can be very cumbersome or not even very useful. So typical use cases for relational database management systems are online transaction processing. Large banking institutions running either DB2 for ZOS or other vendor relational database management systems, financial services, insurance companies, ubiquitous throughout industry. And I'm sure if we ask you what industries you all are in on the phone that said that you use a lot of RDBMS, I'm sure we would probably have, a half dozen to a dozen different industries across the board. Some extended use cases for relational database management systems are data warehousing. So the ability to take this data and reform it in a star schema or some other format so that it can be easily queryable. So this accommodates some of the index technology that we just saw. We are going to reformat the data so that when we ask questions that our analysts want to know about, market basket analysis, the customers that we have that have multiple insurance policies with us, if we're an insurance company, life, health, auto, or other types of cases like that, our sales by city, by state, by region, by country over different time slices, that would be OLAP or online analytical processing. These are all different ways that we can use the RDBMS. Now, what are the issues and limitations? I mentioned the strong data typing and also the rigid schema. I have a defined set of characteristics for each table, the number of columns. I either have to have a representation for that column for every row, or I have to set that data to null. As business requirements change, as new laws are passed, as we have more opportunities with our customers, it's very difficult to, in an agile fashion, change the data model for the RDBMS to accommodate either new transaction processing or analytical needs. The other thing that's important to understand about the RDBMS is that the unit of transfer are pages from disk to memory for processing. Pages in the IBM world can be 4, 8, 16, or 32K, which in terms of billion row tables are very small units. And it means that I need to have a lot of memory in order to transfer the data from disk to memory if I'm scanning most of the data in a billion row table. And so I could run out of memory pretty quickly. So there are problems that are becoming more and more obvious as the volumes of data grow, the V in big data. So at billions of rows in a table, the B tree index becomes expensive because I have more IOs to perform to walk down the index to find the records that I want. I'm also copying the data, making another, I could spend as much as 50% as much disk space on indexes as I do on the raw data. There must be a better way. And so we're going to talk about what some of those other choices are. So one is Netezza. IBM purchased the Netezza product several years ago. Netezza took a radically different approach to scanning large amounts of data. Netezza is also known as PureData System for Analytics. It is an appliance. You buy integrated hardware, CPU, memory, all come in a server in a box that you wheel in, plug into your network, and start using relatively quickly. So you have the advantages from an operational standpoint of not having to do a lot of systems integration, hardware, operating system patches, install the database patches, etc. Some of the key concepts of Netezza are something that I mentioned before, the Field Programmable Gate Array, or FPGA. Then we'll also talk about data slices, distribution keys, and zone maps. So this is the heart of the way that a Netezza would process a query, and we're going to break this down in pieces, and I'm going to get my highlighter back again. So I have a query that you see in the upper left. It is select district product group sum from monthly prescription territory data, where the month equals a certain value, the market equals a certain value, and a specialty. So ordinarily, the way that a query like this would be parsed is that an optimizer in an RDBMS would search for an index on things like month or market or specialty. But the way that Netezza works is that the query is actually vended to the FPGA core, and there are in some machines dozens of these FPGA cores that read the data as it streams off of disk. So I'm going to look at a slice of the data, a data slice for the monthly prescription territory data, and as that data is streaming off of disk, I'm going to apply the uncompression of the compressed data. We usually get 4-by compression. So uncompress the data, select the columns that are in the select clause and project them so that I immediately eliminate columns from the table that I'm not interested in. And then I apply the where clause predicates and am able to filter the data by row for only the data that meets the criteria that I specify. If I have any higher order processing, such as joins with other tables or aggregations or sums or things like that, these can be done in an accompanying CPU core. So the huge differentiator is between a traditional RDBMS and the Netezza is that instead of taking the data and moving a page of data, which contains rows that I'm not interested in, or columns that I may not be interested in, moving that into memory and then operating on that data in a centralized memory store, what I'm doing is I'm taking the query and I'm moving it as close as possible to the disk to uncompress, project, and filter the data as it's being read, and I can process this at 130 megabytes per second, I believe. So very, very quickly scan large units of data. So we can see here, I said 130, 120 megabytes per second for the N1000. The N2000, which is the Striper version of the database, we could scan as much as 325 megabytes per second by reading from multiple disks simultaneously into the FPGA core. So the benefits of the Netezza are that there is no data modeling. We don't have to go through the star schema exercise to optimize the format of the data as it's stored in the relational database to accommodate the queries that are going to be asked. There are no indexes, so we don't have to worry about creating indexes or storing indexes or walking indexes and performing index I/O. There are no materialized query tables. There is no multi-dimensional clustering, no table spaces, no pages, no blocks. All of that goes away. There's only one partitioning strategy if I want to distribute the data throughout the appliance, and that's the hashing algorithm.
And one thing in here, Frank, too, I think that we don't cover particularly in this presentation, but one of the things IBM did initially to address this whole data warehouse thing was to come up with the industry models that were specific for data warehouse models for different industries. When you're doing something like Netezza, and when we put this, in fact, when Frank put this presentation together, one of the things that we have said repeatedly, not just to our customers, but also to IBM, is that sometimes when you're drilling down so much on the industry and a particular business use case for a customer, you're overlooking the fact that in a lot of cases, data is data. And so one of the things that Netezza did brilliantly, and before IBM acquired them and before they've been such a success for IBM, is that they sort of allowed you to bypass that whole modeling exercise, which for a lot of organizations is huge.
I think that's a great observation, that you can treat data as data and you are not trying to force the data into a template or a pattern. So a data slice is how Netezza stores data on disk. Tables are split across data slices. Netezza stores the data on disks in groups according to row. You can affect how the data is stored by using something called an organizing key. The data is compressed according to identical columnar values, so it uses columnar compression, and a hashing algorithm identified by something called a distribution key distributes the data to primary partitions across the disk. So, for example, I could co-locate data from multiple different tables onto the same disk. So if there are tables that are always joined together, such as purchase order header and purchase order line item that both use purchase order number as an identifier key, that data can be located together, so I'm not needing to broadcast data within the appliance when I need to do a join. The data is mirrored, so there's no single point of failure. So the distribution key allows the co-located joins that I just mentioned. Commonly joined tables such as dimension and fact tables of a star schema would use the same distribution key. In this case, we're looking at customer key in both the customer and the orders table. So rows from different tables with the same key are stored on the same data slice and will be filtered by the same FPGA. Zone maps. So an extent is the smallest unit of Netezza disk allocation, and that's 3 megabytes. A zone map is an internal structure to show the range of minimum and maximum values for keyed columns within each extent. So let's say I had a key on last name, and I could say, show me the lowest and the highest last name found in this 3 megabyte extent. I could filter out data that falls outside or extents that don't cover the data that I'm looking for. So let's say I'm looking for Williams, and the zone map says the range of last names that are covered in this particular extent are from Aaron to Baker. I know I can skip that extent without having to look at it because I know that there aren't any Williamses in that zone map range. So this allows me to reduce I/O by skipping extents that don't qualify based on the predicates. Zone maps are internal to the system and require no administration. So you don't have to define zone maps, you don't have to reorganize zone maps, you don't have to do any of that stuff. And these are especially useful in ever-increasing key value data warehouses where query predicates use that key. So let's say patient ID, which I assign by incrementing 1 to each new patient, or order numbers or things like that. So an example from a zone map is I have a zone map built on date and customer ID, and so I can see that extent number 2 covers a range of dates from 01 to 03. Well, my predicate is date is equal to 02, so I know that I only need to look at extent number 2 to retrieve the data that will qualify for the where clause predicate that I've specified. So I can completely eliminate having to read the other extents. So the issues and limitations of the Netezza approach. Rigid schema and strong data typing, very similar to the relational database. Something that we call schema evolution is not easily accomplished on a Netezza. So if we have to add columns or we need to expand the database to allow new functionality, this is not as easy as we would like it to be. And Netezza is definitely not designed for OLTP. It does not optimize data manipulation language, DML statements for inserts, updates, and deletes. So by all means, the Netezza is optimized for data retrieval. So if you have applications that are read mostly, that are data warehousing applications that involve large scans, then the Netezza would be a good choice. Now, how can I combine the best of both worlds? And there are a couple of ways to do this. I'm going to talk about one that's available on the mainframe today. I talked about DB2 with BLU Acceleration and the HTAP that I had done at the last webinar. So in many shops, I would want to be able to accommodate both OLTP, online transaction processing traffic, my customer orders, and banking, ATM withdrawals, credit card authorizations, and those types of things. At the same time, I'm performing deep analytics. Well, why would I want to do that? Well, for fraud detection, for one. I would want to be able to identify a credit card transaction that may be fraudulent at the time that the transaction is being made, rather than 3 days from now when the data has been ETL'd into a data warehouse, and I'm able to look at it and say, hey, we probably should have stopped that, except that we didn't, and the money is gone. So the IBM DB2 Analytics Accelerator is available on the IBM mainframe, the Z13 and the early EC12 models. And I can combine the RDBMS, DB2 for ZOS, with the Netezza Accelerator in a combined heterogeneous platform using something called heterogeneous scale out. So I can get the best of both the large-scale data scanning capabilities of the Netezza as well as the OLTP of the DB2 for ZOS. There are a series of steps that are determined whether or not a particular query will run natively in DB2 for ZOS or will be offloaded to the IDAA. There are a couple of heuristic determinations that are made, such as the size of the tables involved. If I have some very small tables, it doesn't make sense to incur the overhead to offload to the analytics platform. If I'm doing a single row fetch on a key lookup, then I'm not going to move that query off. I'm going to do that natively in DB2 for ZOS. If the query doesn't contain any grouping or aggregation, if the query doesn't contain a predicate at all, if I'm scanning an entire table, that won't be accelerated. So I have a checkpoint here, and I'm not going to be able to do the Q&A as interactively as I usually do, but I want to bring these up just as refreshers. The hashed distribution keys to distribute the data via keys such as purchase order number or patient ID and co-location of data is similar to what DB2 for Linux, Unix, Windows technology. And if you're familiar with that platform, hopefully you would say the data partitioning feature, which also uses a hashing technology to co-locate data for joins that would prevent the broadcast of data within the DPF architecture. Zone maps are somewhat similar to what DB2 index component, and they are somewhat similar to the leaf pages. Instead of containing all of the key values for every row, they contain the minimum and maximum of the values found on a particular extent. So the leaf page contains a RID or a row ID for each different key value, whereas the zone map is a minimum and maximum key value for a 3 megabyte extent, but somewhat similar in that they're leading you to the data itself by giving you ranges of key values that you can find. So the bottom line is, from Milton Friedman, there is no such thing as a free lunch. If we're going to scan lots of data, we need some mechanisms that help us do that, and the distribution keys and the zone keys help us in the Netezza box. So before I go to BLU Acceleration, given the fact that we've talked about doing OLTP and analytics processing on the same platform, I wanted to bring up our second poll, which is, do you run OLTP and analytic workloads together on the same platform? So it could be something like the fraud detection that I mentioned. It could be market basket analysis as customers are checking out of the grocery store. It could be for insurance purposes. It could be to help your customer service reps identify better telecommunications plans based on the minutes of usage and the data that's downloaded. So I'm going to put this question up. I'm going to launch it. Do you run OLTP and analytics workloads on the same platforms together? And be interested in the answers.
So the corollary to this that I should have added was, if you do run both together, is this something that you've started doing in the past year or two, or is this something that you've done historically? Not a question that I added, but one that would be interesting to know.
Well, we know it's split 60-40. Most folks have responded, and interestingly, that's a pretty good split of both analytics and OLTP running together versus keeping them separate. So thank you for your responses, and now we will move on to DB2 10.5 for BLU Acceleration. So BLU Acceleration was released about 2 years ago, April of 2013. That's what's ringing a bell to me. So it's been around for a little while. So it was important for the ability to run mixed workloads to have a data engine that could do both. So on the mainframe platform, IBM used what we call heterogeneous scale-out to provide HTAP, hybrid transaction and analytical processing. Here, what the folks that developed the DB2 for Linux, Unix, Windows, which is a completely different code base that developed in a different lab in a different country, the DB2 for LUW, Linux, Unix, Windows, they decided to, within the same database, combine the ability to perform OLTP and analytics at the same time by having two different methods for storing table data. So BLU Acceleration is memory optimized. Now, this is not an in-memory database. It is memory optimized, but it performs better if most or all of your table data can be stored in memory. So we're looking at servers that have the capacity to have a terabyte or more of memory. The compression that is used is something called actionable compression, meaning that the data can be evaluated without decompressing by using the column cardinality, or the number of occurrences of the values within the column. The SIMD processing, single instruction, multiple data, allows me to look at multiple different pieces of data while executing a single instruction. So I can get much greater parallelism. This is a function of the hardware. This is supported by Intel and some other vendors. So this is something that BLU Acceleration exploits. It's not something that BLU Acceleration does natively or automatically. And then finally, data skipping allows me to skip unnecessary processing of irrelevant data. So BLU Acceleration is a hybrid that supports mixed OLTP and analytic workloads. Column organized tables are the default type within a BLU Acceleration database. The default page size is the largest, 32K, assuming that I'm going to have lots of data. Data is automatically compressed. You have the choice of storing data for OLTP to organize by row, or you can say at table definition time, on a table-by-table basis, I'm going to organize by column for analytics. And there is a DB2 convert utility that allows you to take a row organized table and move it to a column organized table. So an example of column-oriented storage, here I have a query which is not very meaningful. Select C4 where C4 equals X. Surprise, surprise, C4 equals X. Only X is returned. But if I did have this query, the only column of data that I would be interested in this table is C4, so I can eliminate by not looking at the data that's in different buffers in memory, C1, 2, 3, 5, 6, and 7. So I can avoid evaluating a lot of data that's not of interest to me. And if you think about transaction processing versus analytic processing, I may have 50 columns in a table, but I may only be interested in 3 of them in real life. So it makes a lot more sense to only focus on a few columns as opposed to all the rows with all the data, which on a percentage basis, I'm passing a whole lot of data that I'm not interested in. So the SIMD processing that I mentioned before, the single instruction multiple data, here if the instruction is to find all the values for 2005, I can see on the left, I look at 2001, 2002, etc. As the data is read from the blue line at the top. However, if I look at the processor on the right, which is enabled for the SIMD processing, 4 pieces of data are applied each time the instruction is executed. So I was able to look at the data that had been arrayed up top 3 times as fast, or doing in 1/3 of the amount of time, because I was only executing 3 instructions instead of 12. The data skipping, I am provided a synopsis, which is automatically created and maintained as the data is loaded or inserted to column organized tables. They are a persistent store of the minimum and maximum values for sections of the data as they're stored. The issues and limitations, we have the rigid schema and the strong data typing as we've had with the other three models. And the columnar tables are optimized for read mostly. So I can perform transaction processing, but I'm not going to get the same level of performance that I would for a row organized table. So the checkpoint questions, which two technologies so far focus on analytics, that would be Netezza and DB2 with BLU Acceleration. Why do the following matter? The number of columns in a row and the ratio of columns retrieved to the columns in the row. The reason that that matters is I may determine that my analytic processing could benefit from a column organized table if I have 50 or 100 columns in a row and I'm only looking at 3 of them. So if I'm looking at 1.5% of the number of columns in the row, it may make sense to organize the table differently. I think we have 2 more questions. DB2 10.5 is similar to the IDAA as a hybrid platform. 10.5 uses different data stores within the same database, whereas IDAA uses heterogeneous scale out. Some additional factors to consider when looking at standalone Netezza versus DB2 10.5 with BLU Acceleration. Look at the ETL processing, the extract, transform, and load processing between the OLTP and the analytics databases. You may not have the ability to introduce latency of hours or even minutes to move the data from a database where OLTP is performed to standalone Netezza, whereas you can have both of those on a near real-time basis in the DB2 for BLU Acceleration. Look at your existing skill sets, look at the benefits of an appliance versus the hardware-software integration that you're going to need to perform. And then finally, BLU is currently a single node solution. It doesn't have a data partitioning feature at this point. So there is a 10 terabyte practical limit for a database, 10 terabytes of raw data compressed down to 1 terabyte of compressed data. One more checkpoint question. The data skipping that we talked about in the Netezza is exactly like the data skipping sounds like the Netezza feature zone maps, data skipping that's available in DB2 for with BLU Acceleration. So finally, Hadoop. Hadoop is a open source data management technology. It is in IBM's BigInsights distribution. InfoSphere BigInsights is IBM's distribution of open source Hadoop with a lot of other bells and whistles. It was originally inspired by Google's MapReduce technology. Google needed to be able to place ads during searches on a near real-time basis within seconds and needed to be able to crunch a lot of data very quickly and define the MapReduce technology. It is very batch-oriented and read-intensive. It is a shared nothing technology. It exploits the Hadoop distributed file system, which provides high aggregate bandwidth across a cluster and manages data across individual nodes in the cluster. So a MapReduce schematic, I would have a service job that would kick off. I would distribute that job to multiple nodes within the cluster. Each of those would map the data based on its characteristics, and we'll see an example of what that looks like. The data would be aggregated or reduced and then restored together, and a result would be passed back to the calling application. So why do you want to use Hadoop? Well, one reason is that disk latency, the speed of reads and writes on disk, has not improved on the orders of magnitude scale as have CPU and RAM and disk capacity. So the other parts of the computer are getting faster than, on a proportionate basis than disk is. So one of the ways to solve that problem is more disk. The volume, variety, and velocity of big data. So the variety of data, the fact that we're looking at data that may be Facebook posts or tweets or other social media, unstructured or streaming data that we didn't have to deal with before. The volume is the fact that we generate as much data as been available in human history every 18 months now. And the velocity of data, the fact that I need to know now. I can't wait until tomorrow or the next day to try to catch a fraudulent transaction. Solid state disk is fast but very expensive. Schema on read, which is the ability to identify the context or the meaning of the data as we read it, as opposed to the rigid schemas that we apply with the data in the other technologies that we've looked at, the RDBMS, the BLU, and the Netezza. And finally, the store and access paradigm can't accommodate the real-time processing. So I can't get data out of my, my stream and sort the data and organize it and apply a star schema and then load it into a data warehouse and then be able to examine it for actionable characteristics. Google search advertisements, stock trades, and sentiment analysis of tweets all occur within seconds. So here is a conceptual example of Hadoop. I have as my input the animal words that you see there, or the outdoor words of deer, bear, river, car, etc. The data is split based on the records that are received. The data is mapped so that I see one occurrence of each different word in the row or in the record. The data is shuffled so that like records or homogeneous records are assembled together, and then they are reduced so I can see that across all of the different records coming in, I had 2 bears, 3 cars, 2 deer, and 2 rivers, and I'm passed back a final result. This is conceptually what's happening with Hadoop. So, issues and limitations. One of the reasons that I like this slide is every CIO who flies on an airplane and looks in the magazine in the back of the seat and ahead of him is going to come back and talk to his tech people and say, what are we doing with Hadoop? Because Hadoop is hot, it's open source, it's quote unquote free. And so I know a lot of customers are saying we can get away from OLTP, data warehouses, or other forms of analytics, and Hadoop's going to take care of it all. And I, for one, don't believe that. So there's no update in place. There is insert and delete only. I can't do any updates the way that I would update during transaction processing. Hadoop systems are fault tolerant, but there is still the potential for loss. Very simple file compression, relatively immature technology relative to the others that we've surveyed. The underpinnings of relational database management systems are over 40 years old. Right now, there's a skills gap. I hear a lot about skills gap for IBM mainframe databases because a lot of the practitioners are aging out, but a lot of people are implementing Hadoop today and finding people who are just getting out of college and don't have a lot of real world experience. There's a lot of customer integration for Hadoop. You can buy all of the different component products, Jackal and Hive and Hadoop and a menagerie of other products that you can put together in order to get the administration and the analysis that you want out of Hadoop. But that takes a lot of time and could be very expensive in people costs. Or you could buy an integrated stack like IBM's BigInsights, or even an appliance, PureData for Hadoop. But then you lose the commodity hardware cost benefit and the fact that it's open source, because now you're paying a vendor to do the integration for you. So a checkpoint. MapReduce distribution of portions of the data to different nodes, that is the map, and then reassembling them. The answer set is similar to what DB2 for LUW technology, and that would be the data partitioning feature. The DPF distributes the data to nodes at load when the data is queried repeatedly. So this favors response time over throughput. MapReduce distributes the data at query runtime. This favors throughput over response time. So a quote from Admiral Grace Hopper, when a farmer buys another 40 acres, he doesn't get a bigger ox, he gets a second ox. So cluster technologies certainly have their place, especially with very large data sets. So I'm not saying that Hadoop is not a good technology, I'm just saying it's not the only tool that you should have in your toolbox. So I'm going to pull up our polls. So the question is, if it were up to you, where would you co-locate your OLTP and analytic workloads? So far, seen a lot of love for the IBM mainframe. Only over 60% have responded, and 100% have said would consolidate it on IBM Z.
Wow. So you're not pushing Hadoop well enough there, Frank. Or BLU Acceleration.
Well, apparently, yeah. It's all about my salesmanship. So excellent. Thank you all very much for responding. So we're going to take a couple minutes to wrap up. We are just about at the end of our time. Kim, any closing thoughts?
Well, I want to make sure, first of all, thank you to everyone that's been attending our webinars, and certainly encourage everyone that's attending to reach out to us and let us know if you have any questions. We would be more than happy to do a presentation specific to your organization's current environment and what you're looking to do. And also, I'd like to make sure everyone knows, as Frank mentioned, we do hear Hadoop is a big buzzword today. We're also hearing IBM push and push and push BLU and the IDAA. And there are specific use cases, and understanding what your organization needs to do and how best to apply the technology options available is so important. And that's where we're an IBM business partner. This is what we do. We've done it for other organizations, and we would be happy to do it for yours. So don't hesitate to reach out if we can help.
So to that end, I'm going to add the how can we help question and give you an opportunity to respond back with some of the ideas that Kim put together in terms of the ways in which we might be able to assist you. I have on the screen contact information for me and Kim, ways to get a hold of us via Twitter, LinkedIn, and email.
And one other thing, we are getting ready. It's July, so we're starting to think about the Insight Conference, and we're planning to host an event at the Insight Conference. We'll be there. Frank will be presenting. If you're interested in joining us at Insight, I think we're going to be doing a champagne tasting. Feel free to shoot either of us an email and say, I'd like to be invited. We'd be more than happy to have you. But then we're also, because we have been doing some IDAA promotion this year, we are planning to host an IDAA, free hands-on IDAA training class in Baltimore in November. There's information on our blog about the class. If you want to attend, you're more than welcome to attend, but you need to be an IBM customer that currently is using System Z, and you are responsible for your own travel expenses. I can't pay for your travel expenses, but I promise you that we will educate you, feed you, and take very good care of you if you get a chance to come and join us.
So thank you very much, Kim. What I'd like to do now is I went through this pretty quickly. I'm going to open the mics. This is always scary. Actually, what I'm going to do is, before I do that, because people didn't expect that I was going to do that, and I don't want to be unfair if you're in a noisy environment, if you use the raised hand icon, there is the ability to raise your hand if you have a question. I will unmute your mic, and then you can ask your question. Everybody on the call will be able to hear it. If you have any last questions for wrap up before we close out the webinar today. I'm not seeing any, so I think we might have covered it as well as we can. Kim, thank you very much, as always, for your help and your insight and for putting this together. Thank you. So thank you, everyone. Have a great rest of your day. Take care.